to be looking at the concept known as numerical analysis. Sounds like a bucket of fun, numerical analysis. But what I want to help you guys realize is how numerical analysis connects to equations and graphing. Okay, but again, this is kind of a specific concept. I quite frankly don't expect that you can already do this. But I think after we go through some examples and such, you'll feel like that you can add this to your repertoire of application. Let's back up a second. What's numerical analysis? I think I have like a little sentence or two at the top. Basically, before we had calculators and computers, numerical analysis was, it's a process. It's a design and analysis of techniques that will give you, and then the fill in the blank is it'll give you an approximate but accurate solution. The fill in the blank is approximate. Okay, now it sounds a little fuzzy, like what? Well, to say another way, numerical analysis is just this entire technique where you end up estimating to get an answer. That's how they would have done it in the old days before computers and calculators. In the new days, it says here today, numerical analysis will still require some advanced thinking, but these equations, you'll be able to graph them. The fill in the blank is graph or graphed. So when you graph your equations, you're going to find out that it's easy to come up with the solution. What's not easy, though, which is why we're going over it in a class like this, is how to come up with these equations. Okay? It's a lot better shown than talked about. You'll see that numerical analysis is basically thinking about equations and then using your calculator to come up with that answer that matches with what it was that's being asked. Did you have a question?
I was just confused about when you said approximate and accurate. So that
I know it does, and I'll show you when we do the problem. But in the old days, there would have been a time where they would have then started to approximate until they can get to the most accurate answer. In the new days, we're going to skip the approximating, and we're just going to go right to the accurate answer. I'll show you. I'm glad you picked up on it. It is kind of weird. There's actually a whole class you can take in college called numerical analysis. So we're just kind of scratching the surface a little bit here. But look at example 1. Look at example 1. We're going to try to find the area of the largest rectangle that can be inscribed in the curve y equals 8 cosine from negative pi over 2 to pi over 2. Okay, now pretty mathy problem, all right? It's not an application problem about like a roller coaster or about a tsunami like you're doing on your problem set. It's an application problem that's going to require us to do some thinking about equations. And obviously I'm going to guide you through that a little bit. First of all, what does it mean to be inscribed in the curve 8 cosine? Well, we probably need to graph 8 cosine. And before we get a calculator out, I'm going to remind you that we just spent a whole chapter talking about things like this. So let's appeal to that. A cosine graph, even though it's in radians, is still going to do what it's always done. Okay, now I'm drawing purposely just kind of like a solid part of that cosine graph because, well, the solid part that I drew is from negative pi over 2 to pi over 2. Now, if those numbers are kind of catching you a little off guard, you're like, whoa, what's negative pi over 2? Well, that's the same as negative 90, and pi over 2 is the same as 90. We haven't talked about that too much with graphs, but we're going to start to sprinkle it in. So it's the same cosine graph. It's just that instead of it being in degrees, these checkpoints here are in radians. Okay, don't worry too much about that. I'm kind of helping you through it. What I do want you to realize is that that's the 8 cosine graph, and a rectangle that's inscribed, if you've never heard that language, it would be such that the vertices of the rectangle are defined by the graph. Basically, the rectangle is inside of the cosine graph. And again, to be inscribed means that the vertices are on the actual equation. Okay, now that rectangle I just drew, what you want to realize is that that's just symbolizing. It's symbolizing some rectangle. So you see, we want to get the biggest one. And we really don't know if the biggest one is the one that I drew. Or maybe it's this one. Don't draw this, most likely. It'll just mess up too much stuff. But I just want you to realize that that's the goal of this problem, to figure out which rectangle is the biggest. Okay, so the one I drew in yellow, don't overthink it. Like, don't try to figure out exactly how big it is, because we don't know. That's the point of this problem. All right, now if we don't know how big this rectangle is, what we need to do is start thinking about an equation. And that's the next step. I think I have it down here as kind of step 2, where we're going to try to write a formula. And of course, the formula has to match the problem. In case you missed it, the problem is the area of a rectangle. Now, the formula for the area of a rectangle is length times width. Even though that doesn't seem like I'm saying too much, that's a good starting point. Because now what we want to do is we want to start to think about the length and the width. Now, here's the thing. I don't know the length and the width. Okay, but I'm going to start to describe it. And so this distance that I'm marking here, it's an unknown distance, but take a look. It starts at the origin and it ends on the x-axis. Way back even in Algebra 1, you called a distance like that x. Okay, so it's a perfect choice because it's a horizontal distance measured from the origin. Why are we doing that? Well, because now we can describe the entire length from here to here. The entire length. If this distance here is x, you can say the same thing about this distance. So what's true about the entire length? 2x. 2x. Make sure you play along because I have pieces of this problem kind of designed for you guys to play a part in. Okay, now 2x is the length. We also need to get the width. We'll call that distance the width. It's unknown. You'll realize we don't know what it is. It's a vertical distance. A vertical distance has always been described as a y distance. So it's a perfect choice. Now, here's something that you'll realize, so I'm going to share it with you. I don't want two variables. Not going to work. Right now I have x, and then y stuck its nose in here. So what we need to do is we need to think about how can we describe the letter y without using a new variable. What does y equal? What does y equal? This is sometimes one of those things where it's kind of like right in front of you, but sometimes it's so close that you miss it. What does y equal? Don't miss that again. And I don't mean that like in a mean way, because it's kind of like, oh man, yes, of course, y equals the equation. That's always been true since the first day you started talking about graphs and equations. Here's the cool thing today. We have two dimensions, the length and the width. They both have the same variable. So they create a formula. They create a formula. You say, what formula? They create a formula for the area of this inscribed rectangle. Okay, now this is numerical analysis. This is creating an equation, or as I said, an advanced equation. Let's simplify it before we do the other half of the analysis. So if you simplify 2x times 8 cosine, you are allowed to multiply these coefficients to get 16x cosine x. So we have the area equaling 16x cosine x. I want you to sit on that formula just one more moment. This is sometimes the part that kids miss, and then they're asking questions about like the new problem that we're going to do. So sit on this with me for a second. This formula gives the area. It gives the area based on different x values. Okay, that's exactly what this rectangle is about. What area am I going to get based on different x values? You know, as x changes, the area is going to change. That's exactly what this formula says. So in the old days, they would have started guessing. They would have started approximating. Like, what do you get if x equals 1? I don't know. Plug in 1. What do you get if x equals 2? I don't know. Plug in 2. Except they probably wouldn't be plugging in 1 and 2, because look at your x values. They're not going to go beyond pi over 2. But you would have started plugging in numbers until you arrived at the largest area. That was in the old days. Sort of in modern times, we have a calculator, a graph. We have a graph that can show us all the areas based on x values. Think about that with me for a second. That's what every graph has done for you since day one. It shows you all the y values given the x values. Okay, so what we're going to do is you got to kind of be thinking with me here about what I'm graphing. I'm actually graphing the area formula. That's the first thing to notice. I'm graphing the area formula. But I want you to realize why we're graphing it. Okay, because we want to see all the outputs with each input. We want to see the area depending on the x value. Okay, so, and this is the way you always do one of these problems. So we're typing in 16x cosine x. Now, I sort of hate to break this to you, but there's a little more to this than just hit the graph button. And this is kind of the part that kids don't like because, well, you have to think a little bit. I'm talking about the window, okay? If we don't change the window to make sense, we're not going to see anything. Actually, the first thing we really should do here is we should change this problem, we should change the mode to radians. Okay, now the reason we're doing it in radians is just because that's the way x is being measured. X is measured in radians just because that's the way the problem is given. Okay, now if you go to the window, I have no idea what it is. It might be a window from yesterday, from last week. Hopefully it's not a broken window. What kind of x values should we put in here? Are you thinking x values? Yeah, it's the way we design the problem. The x values only go between positive and negative pi over 2. So you can actually type negative pi over 2 for the minimum, and you can type pi over 2 for the maximum. Listen, the scale, in case you've maybe wondered, it doesn't matter. That's just the visual appeal of your graph. The scale is just how much each hash mark's worth. You say, but it's 90. That's like an angle, or that's like a degree angle. It doesn't matter. I'm honestly just going to skip that because I could write it as 90, 900. I could write it as 9. The y window. Now, here's what you have to understand. The y window actually represents the area window. And that's something we are trying to find. Like it's unknown. So yes, we actually don't know what to put in here for the y window. But we need to do a little bit of thinking, sort of some smart thinking. First of all, the area would never be negative. Okay, although I'm going to keep this negative because I just like to see a little bit. It helps students to see the graph. But technically, you don't need a negative. You don't need to go below 0. The maximum ends up being a little bit of a guess. I hate to kind of say it that way, but it is true. It ends up being a guess. Don't do this and say, well, then I'll type in like 1,000 because then I'll certainly see it. What happens there is you just went up to the moon and you're trying to look down at this cosine graph. It's probably way too far away. Okay, now I did a little bit of playing around. I'm going to tell you that if we only go up to 10, we'll see the area. And if you're saying, well, how am I supposed to know that when I do it on my own? I often will give you a hint, okay? But the truth is, if 10 was too small, then I can bump it up to 20 or to 50. Okay, but I'm trying to teach you not to just zoom way out because you might not even see anything. Well, that's good thinking, but the thing is that this is the equation we're graphing. And so, there's some stuff in this equation that I don't expect you to understand. But we make a good guess, or we take a little input from the teacher. And I like that you're thinking about that. That's good. All right, did you change it to radians? And hit the graph button and see if you get a pleasant surprise. Now, just like Owen kind of said here, the graph that you guys are looking at is actually the area graph. Okay, what does that mean? It's the area graph. Go ahead. Well, you have to save that for calculus. If you did that kind of stuff in physics, I'm not trying to find the area under the graph. I'm honestly just trying to understand that this graph is the area. Here, let me show you, because this is good. This is why we're doing this slowly. If you trace along this graph, you will get different areas, like an area of 0. Of course, if I have an x of 0, that means there's no rectangle. But what if I have an x value of, I don't know, like 0.5? Okay, and it's just kind of an x value. If I have an x value of 0.5, look at the area that I got. I got like 7. Okay, well, every x value along this graph will output an area. Are your eyes kind of taken to the maximum? That's the place where I have the largest area. Now, it looks like that is close to 8.9. I kind of wonder, should it be like 9, like perfectly? There's a function on your calculator that will calculate the maximum. It's in the second trace menu. Second trace. It's the calculate menu, option 4. Now, you might want to just watch if you've never used this before, because you get this left bound, right bound sort of syntax. Now, left bound in the lower corner there with a question mark beside it is asking you to move the cursor a little bit to the left of your maximum. So what I do is I move like 2 or 3 notches to the left, and I'm going to hit enter. When I do that, I get a little boundary marker. And then it says right bound, so I'll move a little to the right. And I'll hit enter. And then I'll put it back in the middle and make a guess. It's called left bound, right bound. You sort of define the boundaries, and then you put the cursor back in the middle. It turns out that you actually get the answer that we kind of found before, but I want you to understand what this means. I want you to understand what this means. And simply put, this is the x value, like literally the x value of this rectangle. This is the x value that produces this area. In fact, this maximum area, which I think if we read the question carefully, was what we were trying to find. I usually ask you to make a little statement or at least interpret your answer. And so I put a couple words beside these numbers, which shows that I understand that that's the maximum. I don't think the question actually asked us to give the x value, but it doesn't hurt to talk about it. Not something that you just kind of can find by looking at this sketch. Okay, this number 0.86, I mean, who would have guessed? But that's the size of x that will produce this rectangle, which is the biggest one inside 8 cosine. Numerical analysis. Okay, by the way, this was the part that instead of approximating, we found it right away. But again, somebody would have had to guess 0.6, 0.7, 0.8, and eventually they would have seen that this is the biggest number. Let's do another one. There's a lot that you saw here. There's some things you still need to see. Once you read this one, maybe read it twice. Irrigation canal. Maybe you just kind of want to get it done. And I'm going to walk you through it, but it doesn't hurt to understand what's happening here. We're trying to figure out what theta, we're trying to figure out what angle is going to give us the best canal, like the most space. If you think about it, should the angle be like really small, like the canal is like flat and wide? How much water is going to fit in there? What if the angle is like 45 degrees? What if it's 90 degrees and we just have like a square canal? Okay, the question is, what angle is going to give us the largest space in here? Now, it uses the phrase cross-sectional area. It's a little fancy, but basically that means that we're just trying to think of the area of a trapezoid. And so we start with a formula, just like the other problem. Except, do you remember the area for a trapezoid? I don't either. Okay, you can look it up. It's not the purpose of this activity. The purpose is to think about numerical analysis. The area of a trapezoid is 1/2 the height times the sum of the bases. It might sound familiar, maybe not, but that's your area formula. Now, I'm going to take you somewhere, and I think you can get there, and that's why I'm bringing it up. This area formula has an H, an A, and a B. I don't want that. I want it to have a theta. I want my area formula to be in terms of theta. So as theta changes, I can think about the area. Now, this is a little fancy, but we're going to one by one, we're going to change each of these variables. Okay, so ready? We're going to think about H. Now, to help you do that, I'm going to guide you a little bit. Pretty fancy, eh? I just put H into our sketch. I'm sure you see the right triangle, but what I want you to realize is it's now time to do something that relates these three variables. Well, they're not all variables, but these three values. Here's something. It's not that cleaning machine that they're cleaning up the A-wing. It's now, I'll just kind of say this because I'm being honest with you. Everybody should be able to do this. And you might even be like, yeah, we did this a couple times. Yeah. How does theta, H, and 8 relate? Everybody should be able to do it. Which trig function out of SOHCAHTOA? Good. What's it look like when you write it as a formula? I'm sorry, you might have already said it.
Oh, wait. No, from here.
So the sine of theta. Okay, you're close. You're on the right track. We just want to write it as opposite over hypotenuse. Now, if you're saying, yeah, I can do that, but why are we doing that? Watch. This is the part where I want you to get this. What does H equal? Well, look, it equals something with theta. You say, what's the big deal? This H right here, in a few moments, this H is going to become something with theta. Remember, that was our goal. Okay, I'm going to wait to replace it, but we're on the right track. A. It's one of the parallel bases. It's already 8. By definition, A is one of the parallel bases. Now, I didn't use theta because I didn't need to. I could just define it as a really nice constant. So why not? So the letter A, in a few moments, it's going to change. It's just going to become the number 8. B. It's the other parallel base. Ooh.
Never mind.
This is exactly what I want you guys to do. Feel free to chime in here.
Yeah, hear me out. Would it be 8 sine or 8 cosine theta plus 8?
Wow, you're really warm. Okay. Talk to me about the plus 8. Let's go to the last thing you said.
Well, then each side is 8 and that rectangle dash towards 8.
Justin?
So I think it's like 2 times 8 cosine theta plus 8.
You are correct. Now we need to go back a little bit because people are like, whoa, okay, go back a step. I don't know quite how you were thinking, but I'm wondering, what do you think about those pink distances? Like, can you take us into your mind? Okay, good. Good.
I forget the word you use, the angle of the bottom is the angle of the top.
All right. Now, don't worry about like what you have to use, but I find this is the part that's hardest for kids. I'm going to do something just because I want to make sure you guys hear this. You don't know how long this is. Okay, you don't know how long it is. This is new kind of thinking, though, to be able to say, then I can call it X? Sure. You can call it X so that, and I know you guys all heard Justin say cosine, but so that you can make a statement. Okay, now, do you guys see how those 3 circled variables relate? They relate again with adjacent over hypotenuse. Now, I'm just taking us back a step from what you heard him say so that we can all say that X equals 8 cosine theta. In other words, this pink distance is 8 cosine of theta. Now, if you take a little bit of what Reba said and a little bit of what Justin said, we can all say what B equals. Okay, now remember, B is supposed to be this entire distance. So we end up with 2. We end up with 2 of these 8 cosines. And don't forget the 8. Don't forget the 8. All right. Simplify. Always simplify if you can. So we have 16. But we want to realize that it came from 2 of those plus 8. Okay, I'd like to give you a little time to process, but we have to keep moving. We're going to change this equation, this 1/2 HAB, to now all of a sudden be all about theta. All you got to do is just replace H with 8 sine of theta. So H is 8 sine of theta. Replace A with an 8 and replace B with this big bad thing, 16 cosine plus 8. This is numerical analysis. It's kind of analyzing a problem, as you can see now, in terms of theta. And since it's in terms of theta, the cool thing is that my area, my output, well, can be analyzed based on different angles. By the way, this whole thing can be simplified, right? I mean, always simplify before you go to your calculator, your last step. Half of 8 is 4. We also have some like terms. We have some 8 plus 8 going on. So simplify that puppy and looks a lot nicer. That's a formula that gives the area based on theta. Back in the old days, you'd plug in some different angles, you know, like 30 degrees or 45 degrees, or who knows, maybe it's some just really random degree. And that's why that would be a pain in the neck to have to like approximate. In the new days, we can graph it because your graph will show you all the outputs based on the input. Now remember, the input is theta, but we have to type x into the calculator. The input is theta. Here's the part that kids don't like. The window. Maybe you do like it because you're starting to catch on. You have to think. Let's think. Think about x. X. Oh, x is theta. Angles. 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 What kind of angles would we want to be like looking at? It's good. Now, what I'm going to say, though, is in theory, ready? In theory, my angle could go past 90 and it's still a trapezoid. You might say, well, what kind of canal is that? Well, in theory, I can go the whole way to 180. I'm actually going to go to 180. But I like what you said, Hannah, because you're thinking about angles. The y-axis. Make sure you don't hear me wrong, but I'm an honest guy. The y-axis is the area. We don't know the area. That's the whole point of this problem. So, yeah, we kind of don't know what numbers to put in here. Okay, we can play around. If we put in something too small, it can get bigger. Or we can take a little advice and we'll put in 100. But how did I get 100? Because I played around. And if I didn't see the answer, I just went a little greater. Don't just type in 1,000 or 10,000. You'll be on the moon trying to see the irrigation canal. All right. Well, if you hit graph, whoa. It's like the New York skyline. We're in degrees. You say, how do we know we're in degrees? Because that's how x has been defined. X has been defined to be between 0 and 180. X is in degrees. Your equation's in degrees. Your mode should be in degrees. Now be careful. That's not a sine wave. That's a 4 sine times 16 plus 16 cosine wave. So, I don't expect you to know what that graph looked like before we had our calculator, but I do hope that you realize that on this graph are all kinds of angles and the corresponding output. And you should be drawn to the maximum, because at the maximum, we end up seeing that it's 60 degrees. Now, I did something a little different here. I didn't do left bound, right bound. You can do left bound, right bound, but I noticed that if I type in 60, I get right to that number. I would recommend that you do left bound, right bound to be sure. I just wanted to show you that we can type in, maybe because we have a hunch. Now, it's helpful to understand what it is that you're getting here, like to label it, like literally 60 degrees, and label it as 83 square units, because I should have did that with the other problem, but it's area. And that allows us to answer the question, where you can say max area of 83 when theta equals 60. I forget exactly what it is I asked you to do. I think I asked you for the maximum area, but we can also identify 60 as the angle. Interesting. It wasn't 45. It wasn't 90. It happens to be 60. Okay, because of numerical analysis. Now, on the next page of this little pamphlet is the one homework problem. It's just one homework problem. It has to do with a feeding trough. Okay. You shouldn't just look at it for 5 minutes and say, yeah, we'll go over that tomorrow. But I also don't want you to labor over for like a half hour. But you should spend some time seeing if you can get it. There is one piece of the answer on the last page. Don't look on the last page, but I kind of hid the answer on the last page, and I tell you that, and you can check it when you want to.